So the physical section of the course now, we're going to be looking at energetics, and we're going to see what is an exothermic reaction, what's an endothermic reaction, and how to explain bond breaking and bond making. So let's have a look here. Firstly, we need to think about these three terms, which are very important. As I said, the objectives today eventually will be to draw energy level diagrams for now. Later on, we'll be doing energy profile diagrams when we do rates. But for today, these are the objectives. So no examples of endo and exothermic reactions and the definitions. So the first one, exothermic, means that heat energy is released from the systems to the surroundings. As a result, temperature increases. Be careful with this. A common misconception is to think if energy is released, it's going to cool down. That's actually wrong. So if energy is released, think of a radiator releasing heat. It's going to make the room hot. The temperature is always measured at the surroundings, not the actual system. So you're not looking at what's happening in the reactant, you're looking at the outcome on the surroundings. Endothermic is the opposite. It means that heat energy is absorbed from the surroundings to the system. As a result, temperature decreases. Again, you may be confused. If energy is absorbed, why don't we get hot? Well, because we're not measuring the system, we're measuring what's happening around it. So I want you to think of endothermic as an ice pack. It makes your skin cold. Nobody cares about the actual ice in the ice pack. We care about the effect on the skin, the surroundings. So exothermic means heat released and hot. Endothermic means heat absorbed and cold. Activation energy is the minimum energy that's required for a reaction to occur. Now, system and surroundings, I can draw it for you with a box. If you imagine this being the system, an exothermic reaction will release heat out to the surroundings. So that will be exothermic. An endothermic reaction, on the other hand, will take heat in from the surroundings to the system. So that's another way to think of it. Okay, back to this. Let's look at a basic principle here. In basic terms, what must happen during a successful collision? So during a successful collisions, the particles must collide with enough activation energy. So with enough energy that it is either equal or greater than the activation energy. And the second thing that must happen is that the collision must be in the correct orientation. So if the particles collide at the wrong angle, that would still be unsuccessful. Now, what two steps are involved in every chemical reaction? Well, the reactant bonds need to break and new bonds need to form on the product side. So to summarize this principle, think of having your hands tied by a rope. In order to break that bond between the rope, you've got to have a lot of energy to break it apart. So that's why breaking bonds is an endothermic process primarily. For making bonds, I want you to think of two cars crashing. It's going to release energy. So that's exothermic. Now, because both of these processes occur in every reaction, whichever value is bigger will determine the overall outcome of the reaction, if it is going to be endothermic or exothermic. So, for example, a hydrogen H2 molecule will break its bonds to form two hydrogen atoms. That requires 436 kilojoules. When the two hydrogen atoms combine to make the H2 molecule, they're going to release 436 kilojoules. So it is all a conservation of energy principle. Now, if we expand on those two definitions for exo and endothermic, let's see. 1 second. I will get you the official definition for this. This is the higher tier aspect of this. So if we hone in on this part here, know that bond breaking is endothermic and that bond making is exothermic. Now watch carefully. You could remember this Bendomex, which means breaking is endothermic and making is exothermic. So Bendomex. Now, how do you actually put both things in the definition? Have a look. For an exothermic reaction, the energy taken in to break all the bonds is less than the energy released when the new bonds are formed. Now, it's very easy to get this wrong if you accidentally say less than the energy taken in when the new bonds are formed. So don't mess it up. You have to match them up correctly. So really, you're looking at this principle here. Energy released making bonds is greater than energy absorbed breaking bonds. That is essentially the 2-mark high-level definition of an exothermic reaction. And that's what it says here. Now, the reverse will be true for endothermic. So the energy taken in to break all the bonds is more than the energy released when the new bonds are formed. So all you do is just change this sign. Then it will be the correct definition for endothermic. So it's very important that you know this. As a result, you can do something called a bond energy diagram. So energy level diagrams look like this. So draw and explain energy level diagrams. So if you imagine, let's start with an exothermic reaction on the right. If you start here with your reactants and they release their energy, now they're going to have less energy. So the product will have less energy. And the arrow points down. We call this a negative energy change or a negative enthalpy change. So triangle H officially means enthalpy, which simply means the energy content stored in a system. That's what it means. Now, the endothermic will be the opposite. So you start with your reactants lower, you absorb energy, and now the products will have a high energy. The enthalpy change has to point up, and this time it is actually positive. Now, the reason for this positive and negative, you can think of it this way. A big number minus a small number will be positive. A small number minus a big number will be negative. That's the easiest way to think of it. One more thing to note is the x-axis. Okay, so the x-axis here for both of these has not been drawn. The x-axis should be labeled reaction pathway. Reaction pathway. Don't call it time. It is a theoretical reaction pathway. Okay, well, that covers the basics. However, you should also know some examples of endo and exothermic reactions. So if we go back to our PowerPoint, we can find it. There it is. We should now know some examples of endothermic and exothermic reactions. So here are some pictures. Acid plus alkaline neutralizations are usually going to be exothermic. There are some cases where it is endothermic from metal hydrogen carbonates reacting with acids, but all the other normal hydroxides, oxides, carbonates, they react in an exothermic fashion. Burning a gas stove is obviously exothermic. All displacement reactions are exothermic, and the bigger the difference between the two metals in the reactivity series, the more energy is released. When a metal reacts with an acid, it's a redox reaction, but it is actually exothermic. There'll be fizzing, the metal will disappear, and it will also release heat. Right, that's it for this. Real life examples will be hand warmers, where you squeeze it and it makes warmth, or self-heating cans, or a barbecue stove where you light it with a match, the gas. So these were some exothermic reactions. In summary, we have hand warmers and self-heating cans. We have combustion of fuels. We have most neutralizations and displacements. There's one more really important reaction. So this was the really important one is aerobic respiration. So that one is also exothermic and a good real life example. So just know some of these examples. Now, endothermic is on this slide here. We have baking soda with vinegar. So vinegar is the acid and the baking soda is the hydrogen carbonate that I mentioned. Also sherbet sweets with citric acid and again, hydrogen carbonates, they're endothermic. Ice packs, the one I told you to think of most famously, where you crush the ice and put it on your skin and it feels cold. And lastly, we have the decomposition reactions where you have to put energy in to break it apart. So in summary here, the reactions, the real famous real life one is the photosynthesis, because energy from the sun is absorbed by the chlorophyll. Otherwise, I would just remember ice packs and very famously thermal decomposition. And then you can learn the hydrogen carbonate with an acid. That completes the first part of this. Now, you will also need to know these diagrams, but I'm going to save these for when you do rates. So these are called energy profile diagrams, not energy level diagrams. So we can actually cover these when we do the rates topic, or we can cover it now. To be honest, since it's already here, we might as well cover it now. So in the previous kind of set of notes here, we had what's called energy level diagrams. Now, these ones, which you do need to know for both syllabi, when you do the rates topic at least, these are going to be called energy profile diagrams. So on the x-axis here, you would put reaction pathway. Okay, so it's largely similar. You still have this part and this part, which is the same as the energy level diagram. So in an exothermic, the reactants start higher, they release their energy, and now they have a lower energy as products. The arrow points down, and this is called the enthalpy change or the energy change. Now, activation energy is always going to point up because it is always an endothermic process, activation energy. You have to put energy in. It's kind of like the barrier that needs to be overcome for the reaction to occur. So here it's actually going to always point from the reactants to the peak. And remember, that's the minimum energy required for a reaction to start. Lastly, enthalpy change is going to be negative for an exothermic because we have a small number minus a big number. Okay, so make sure you practice drawing it from scratch. Now, an endothermic diagram would look the kind of opposite way. So remember, the x-axis is still going to be the reaction pathway. The reactants start lower down, they take heat in, and they go higher up as products. Now, you need to understand this key component. Activation energy always starts at the reactants and goes to the top peak. So the most common mistake here would be to draw this and call this the activation energy. Now that's wrong. It's got to start all the way the reactants. And that's actually also shows you the sheer size of this arrow being so big, shows that the energy required to break bonds is greater than what's going to be the energy released forming bonds. Now, energy changes, just like energy level diagrams, it points up because energy is being absorbed. So that means a big number minus a small number will give you a positive enthalpy change. Okay, remember this reaction gets cold. Think of an ice pack. Think of a radiator getting hot. Practice both diagrams. Don't make silly mistakes with the arrows because it is really very easy marks. Okay, now the last part of this topic that is both in AQA and in Edexcel would be the bond energy calculations, which I'm going to go over next. So in order to do a bond energy calculation, I'm going to load up a worksheet right here for you, and we're going to go through some examples. Okay, here we go. That's my sheet. Okay, so these will be attached. I have two sheets that you can practice. And what we need to do is use these bond energy values to calculate what's called the energy change, or the enthalpy change. So firstly, you need to know the formula for this. And the formula for this is going to be, let's see if I have it here written, or I can draw it out for you. There it is. Right, here we go. Formula, oops, is the sum of all bonds broken minus the sum of all bonds formed. So that basically means the left side minus the right side of the equation compared to where the arrow is. So bonds broken will always be on the reactant side, the left. Bonds formed will always be on the right of the arrow, which is the products. So you just need to add them all up and divide. That is actually easier said than done. So let me illustrate this with these reactions here. Okay, I'm going to do number 5 as an example because it is more complicated looking. First thing to note is you should have it drawn out if the examiner doesn't already draw it for you, because otherwise it could become quite complicated. You might miss a bond. So I would divide my page in half, and I would first write BB for bonds broken, and I'll add up all the bonds broken on the left side underneath the reactant side. When you do it, what you should aim to do is tick off each bond as you do it. So for example, 1, 2, there's 2 carbon-carbon bonds. So carbon-carbon is here. So I'm going to write 2 times 3, 4, 8. Then I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. I'm going to write 8 times CH, which is 412. By the way, I should have mentioned this bond energy corresponds to the energy needed to break 1 mole of covalent bonds in the gaseous state. So in simple terms, is the energy required to break a covalent bond. Now, don't forget the oxygen is 5 times O double, so it's 5 times 498. And what I will do is then add all of this up and get myself a value. And that value is going to be 6, 4, 8, 2. Then on the other side of the page, I'm going to do the bonds formed. Now, CO2 and water are easy to make a mistake on if you don't take the number into account in front. There's a 3 here, so you may be tempted to do 3 times 743. Now, that would be wrong because every one CO2 has 2 bonds. So it's actually 6 times 743. And similarly, this is going to have 2 bonds for every 1 water. So if you have 4 of them, it will be 8 times 463. Now, when you add that up, you're going to get a value of 8162. Now, all you do is subtract your 2 values. So you do 6482 minus 8162. And your final value for this will be minus 1680, which makes it an exothermic reaction because it is a negative enthalpy change. And this is a combustion reaction using oxygen to burn propane, which means that it will be exothermic. So that was my example, and that's going to be my only example because ultimately it comes down to you ticking so you don't miss a bond. Otherwise, it's very easy. It's just bonds broken minus bonds formed, left side minus right side. And that's how you find enthalpy change from bond energy values. So that brings to an end. Obviously, practice these worksheets will be attached. That brings to an end the energy that's consistent with both AQA and Edexcel. If you're an Edexcel student, then you should tune in for the calorimetry lesson. Otherwise, the basic part of energetics has now been done. So I will see you guys next time for the rest of this. Yes, so just checking here, for example, on the Edexcel syllabus, this one is. We've now done this. Notice it's in bold, so it'll be your paper 2. We've done everything except these 2 points, because if you're an AQA student, you don't do these 2. So AQA students do all of this. Okay, so you'll do the practicals in school. But this calorimetry part is just at Excel, so please tune in for that. Otherwise, I'll see everybody on the reversible reactions we're going to do next and equilibrium. So see you then.